So we're going to be doing a bit of review here from Math 20-1. In Math 20-1, you sketched angles in what we call standard position, rotation angles. And I hope you have some kind of inkling in the back of your head of what I'm talking about. This is where we have an arm that pivots on the origin and it rotates to some final position, and we call that rotation a rotation angle. The difference is we have to be able to work with rotation angles now in both degrees and radians, and although you're taught about positive and negative rotation angles in Math 20, the emphasis is on positive rotation angles, and now here we have to be able to work with both quite regularly. Once you learn what radians are all about, then basically a radian measure is a way to measure an angle. It's like having miles and kilometers as being two different ways you can measure distance. And if you know the relationship between miles and kilometers, you should be able to convert back and forth. And that's a big part of this unit, is converting from radian measures to degrees or vice versa. You're expected to know what 1 radian looks like approximately. And then we're going to be talking about coterminality, which depending on who you had for Math 20-1, you may have already been introduced to that. All right, let's get going here. A definition. A radian is a very special angle. It's the angle created, the word is subtended, by an arc that's equal to the length of the radius of the circle. What does that mean? It means if you take a circle with a radius, that angle that I'm indicating there is 1 radian if that arc length between the 2 points is 1 radius. So if you were to take a piece of string on this circle and stretch it out so that it is the length of the radius and then wrap that string around the circle, you would be creating an angle of 1 radian. So that's the connection between the words, is that each radius creates 1 radian. Each radius of arc length creates 1 radian of angular measure. So that's 1 radian. I think it's kind of important that you recognize that that's around 60 degrees. It turns out it's a little bit less than 60 degrees, but it's 60-ish degrees. You can see looking at that it's pretty close to 60. Would you agree? Okay. It turns out, and if we had more time, I would demonstrate to you why this is the case, but it turns out that 180 degrees is exactly equal to pi radians. So if you convert 180 degrees to radians, you get not 3.14 radians, not 3.141 radians. You get 3.141592 forever radians. It's an irrational amount. And to illustrate this to you, and I don't know, this helps for some people, so 180 degrees, this is a fact. You need to know this. It's a fact like 2 plus 3 is 5. That's right. Okay. You need to know this. It's the starting point for so much. If you take a look at this diagram, I'm going to let it loop. So we'll just give it a second to go back to the beginning. There we go. So if we draw a circle with that red length being the radius, and then we take that radius and we curve it around the circle, that's 1 radian. And if we extend that and do it again, wrap another radius around, that's 2 radians in total. And if we go a third, that's 3 radians, and it comes up a little bit short of being 180 degrees. That extra amount is 0.141592 radians. So in total, a half a revolution is pi radians, but a full revolution then becomes 2 pi radians. You're with me on that? It's just something you need to know. So complete the following chart. All of these angles in this chart, well, I'll start with the 30, 45, and 60. 30, 45, and 60 are what you call in Math 20-1 special angles. And I don't know if you remember why they're special. They're special because they divide without remainder into 180. Now, if you take a look at 60 degrees, do you agree 60 goes into 180 perfectly? How many times? 3. Well, if 180 degrees is pi radians, and 60 degrees is a third of 180, then 60 degrees is pi over 3 radians. So that's why you have to start off with that thing that I said, that's a fact. Pi radians is 180. And you use that to figure out what all of these are. I could write this. I could write pi over 3 rads. I could. But when you're talking about radians, if there's no unit specified, you need to understand its radians. That's why your earlier math teachers hopefully make a big deal about the fact that if it's 45 degrees, you have to put that degree symbol. Or 70 degrees, you have to put that degree symbol, because if you don't, it means radians. Clearly, 0 degrees would be 0 radians. If you go to 90 degrees, well, 90 degrees is exactly half of 180. And if 180 is pi, we can even do this, right? Why not do that? We know that's pi. We could even do this, 2 pi. But if 90 degrees is half of 180, then in radians it's half of pi. It's pi over 2. And it's just it seems like such a minor thing, and if you've had me as a teacher before, you might remember me telling you this. If I start to see you writing things like this, that vein in my forehead starts to pop out. Write it as pi over 3, not pi slash 3. That becomes an important habit if you do this. It's an important habit to break for later when we talk about algebra. 45 degrees. Well, you know, if you're watching this on video, you can't see this, but if you think of my arm as being a rotation to 180, how many 45-degree chunks are there? I know some of you will want to take 180 divided by 45, but just look at it. 1, 2, 3, 4. So there are 4 45-degree chunks in 180. What does that tell us? It tells us that 180 is pi over 4 radians. Because again, this is your, I don't know, benchmark? I don't know what you want to call it. This is your starting point that you make everything from in terms of these angles. 30 degrees is pi over 6. Now, what's going to happen to all of you is you will accidentally memorize that. I did not think of this when I said it's pi over 6. But if you look at my arm again and you say, well, how many 30-degree chunks are there from here to here? Well, 30, 60, 90. There's 3 in 90 degrees. So there are 1, 2, 3, 4, 5, 6 in 180. So 30 degrees must be a sixth of 180, which is pi over 6. 270 happens to be the following. A pi over 2, another pi over 2, and a third pi over 2. It's 3 pi over 2s. 90 degrees is pi over 2. How many 90 degrees do you go to get to 270? 3. So the first part of this lesson now is about reviewing Math 20 and then also becoming familiar with these angles. And we're going to extend these angles into all of the quadrants. You'll see that in a bit. Quick review of angles in standard position from Math 20-1. I'm sorry, I apologize. Does anybody have any questions with those values? Okay. So again, I think it's important that you think not in terms of dividing numbers, but in terms of dividing that semicircle into chunks. An angle in standard position is called a rotation angle. It's formed by rotating an initial arm around or about a fixed point called the vertex to reach a terminal arm. But so that we're all driving on the same side of the road, mathematically speaking, we have something which is called standard position. So the initial arm with a rotation angle in standard position is always on the positive x-axis, and the vertex, the point of rotation, is always at the origin. So that is an angle that we would call a rotation angle in standard position. Does this ring a bell? Now in Math 20, you kind of confine your work, or you were supposed to confine the work to quadrant 1 and 2. In my Math 20, I kind of cheat the system a bit and I get students to work in the other quadrants. We can work in any quadrant here in Math 30. The other thing you need to know is that positive rotation angles are counterclockwise, which seems non-intuitive, because counter kind of seems opposite or negative. The reason why counterclockwise, which is that direction, the direction that the hands move on an analog clock, the reason why that's a positive rotation angle is so that it will rotate through the quadrants in the order in which they're numbered. And those of you that have taken physics, you understand there's a connection between sines and cosines of x and y coordinates and all of that. That's connected to what we learn in this unit. So now I want you to go to that handout. It's a single handout called Common Rotation Angles. It is on the pink sheet of paper as opposed to your unit handout, which has a peach cover color. We just noticed at the beginning of the class that those two pinks are totally different pinks. So we're going to be looking at that. And starting at 0, we want to move through one complete rotation and label every angle on those points. So one of the things you need to know is that these points are all points that correspond to special angles. These central points here are what I would call the 45-degree reference points. I don't want to get into reference angles today, but those points are exactly halfway between the axes, angularly speaking. Okay? So those are 45-degree increments. The other points, the points that I'm just going to circle in red, and there's no need to circle this, I'm just in instruction mode here. These ones are 30-degree or 60-degree reference points. They are 30 degrees away from the x-axis or 60 degrees away from the x-axis. Okay? And that's important here. So we're going to start labeling these. Obviously, that is 0 degrees. And I thought of breaking this into the top and the bottom so we could make it a little bigger. You're just going to have to, I'm just hopeful that your eyes can see the print that's a little smaller. I think you guys are young, you have good vision, you should be able to see that. I think it's valuable to see the whole thing rather than pieces of it. And that, of course, is 0 radians. So I'm going to be asking you to write the degrees on the inside of this circle and the radians on the outside. We can go over to 180 degrees as another kind of benchmark, and we know that that's pi radians. We happen to know that 90 degrees is pi over 2. Well, we do now. You didn't 10 minutes ago. And 270 is 3 pi over 2. And don't just blindly write down 3 pi over 2. Ask yourself why that's the case. And it's the case because, I just want to get into a different mode here. It's the case because if I were to take an initial arm and rotate it so that it's pointing down, I have to rotate through 3 pi over 2s. And what's about to happen is you're going to find, I really hope, it's easier to think of radians than degrees. It's easier to think of radians than degrees. So when I rotate this from here, I say it's 1, 2, 3 pi over 2s. It's simpler to me. It may not be simpler to you, but I will tell you this, that it will be simpler to you when we look at other angles. The other thing I want to point out, and it's maybe the same thing, is I put all of these up degrees first and then radians. We're going to do the opposite now. Let's focus our attention on all of these. So I'm focusing my attention on what I would call the multiples of 45. Every dot that I've highlighted here with blue is a multiple of 45 degrees, and 45 degrees is pi over 4. These are all multiples of pi over 4. So this first dot here in quadrant 1 is pi over 4. Which is 45 degrees, right? The dot at the top of the screen, we don't need to write anything here, but I'm going to write something down just temporarily. The dot at the top of the screen is 2 pi over 4. If you look at my arm, 1, 2 pi over 4. But if you look at the fraction 2 pi over 4, it reduces to pi over 2. We've already got that one, okay? So what about the next dot? Well, the next dot This is 1 pi over 4. This is 2 pi over 4. Well, this is going to be 3 pi over 4. I'm not saying how many degrees is that and let's figure out how many radians it is. I'm just saying it's 1, 2, 3 pi over 4. If I continue this process, oh, and by the way, do you understand how I got 3 pi over 4? Do you understand that if you understand, finding it is a counting thing, 1, 2, 3 pi over 4. If I say, what is that angle, that's a calculation thing if I ask you for it in degrees, isn't it? It becomes a little bit more work. It happens to be 135 degrees because it's 90 plus 45. But it's easier for me to go, oh, wow, yeah, it's 3 pi over 4. If I continue this process, don't forget this was 1, 2, 3 pi over 4. Well, this would be 4 pi over 4. But 4 over 4 is 1, so it's pi. This would have to be then 5 pi over 4. And again, I can identify that it's 5 pi over 4 with less brain activity than it takes me to go, it's 225 degrees. I have to think about that a little bit more. The bottom here is going to be 6 pi over 4, right? 6 pi over 4, but the fraction 6 over 4 reduces to 3 over 2, so it's 3 pi over 2. It's already included. The next one, if this is 5 pi over 4 I'm pointing at, and then 6 pi over 4, this next one in the quadrant, labeled number 4, well, not labeled, but quadrant 4, would be 7 pi over 4. And again, if you want to know the angular measure in degrees, you got to either go 360 and subtract 45, or take 270 and add 45, and you get 315. Are we good there? This is going to become second nature to you, okay? Or it has to. Now what I'm going to do is focus my attention on these dots. And you can do this in any order you want. I'm just teaching you how to come up with these things yourself. These are all 30 degrees away from each other. And 30 degrees is pi over 6. You can even see up here that this is 0. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 6 pi over 6. There's 6 pi over 6s in there. So that makes this first one pi over 6, which is 30 degrees. It makes the second yellow dot, the one after that, 2 pi over 6. Well, we don't write 2 pi over 6. We put 1 pi over 3. And we don't even have to write the 1, and that, of course, is 60 degrees. So I would like to go through this one more time, just once, and then I won't keep bringing back this huge yellow blob. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, right? We're counting pi over 6s. Well, that makes 90 degrees 3 pi over 6, which is pi over 2. 3 over 6 is 1 over 2. The next dot in quadrant 2, let's count this again. This is 1, 2, 3. This is 4 pi over 6. This number right here in radians is 4 pi over 6. But that's 2 pi over 3. If I wanted to, I could have said, well, 60 degrees is pi over 3, so this would be 2 pi over 3 because there are two 60 degrees in there. You're starting to get the idea here? This next one will be, so again, 1, 2, 3, 4. That's 120, 5 pi over 6. And you can figure out what it is. It's 150. And we just keep going around the circle like that. The next yellow dot, I'm just going to use an arrow to point here as I talk. It's going to go away. I'm not even going to bother. The next one at 180 would be 6 pi over 6. The one after 180 would be 7 pi over 6. which you can figure out the angular measure in degrees to be 210. These are both angular measures. One's just written in radians, one's in degrees. The next yellow dot after the 7 pi over 6 would be 8 pi over 6. It's 4 over 3. If you look at my arm, this is pi over 3. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. When I indicate the pi over 3s, I really exaggerate it by pointing down a lot. I don't want you to think I'm talking about the 45-degree angle. So this is a 60-degree reference angle from your perspective. It's probably more than 60, but I want to make sure you know that's the one I'm talking about. That's 240 degrees. If you want to work in pi over 3s, if that's 4 pi over 3, then this yellow dot over here would be 5 pi over 3. If you want to work in pi over 6s, this was 8 pi over 6, 9, 10 pi over 6, which is 5 pi over 3. Which is 300 degrees. And the last dot here, well, not quite the last one, but the next one is 11 pi over 6. I just know that because it is pi over 6 shy of 2 pi. 2 pi is 12 pi over 6. So I don't rotate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi over 6s. And, you know, if we want to, we can go back, that's 330, we can go back to the beginning and say that that is the same as 360 degrees or 2 pi. This is not a Math 30 example of something you would be asked on an exam, but if you do not understand what these angles are, you cannot do the math that's about to come. So let's take a look at some examples now. Convert the following degree measure to radian measure. So is 75 degrees one of those common angles? What I mean is it a multiple of 30 or a multiple of 45 or a multiple of 6? No, so we have to walk away from that diagram that we just created, and we have to come up with a different strategy. And the strategy we're going to use is, I think, the most useful math tool that anybody has ever come up with. We're going to use the concept of a ratio here. We know that pi radians is the same as 180 degrees. So the ratio of the radians to degrees always has to be the same. If I have half as many radians, I have to have half as many degrees. So all I'm going to do is this. I'm going to solve that equation. I cross multiply, I get 75 pi over 180. I don't want to throw this number into my calculator because I want an exact value, and pi is an irrational number. But what I can do is I can simplify 75 over 180. And if you couldn't be bothered to think about it, then I suppose you could put 75 divided by 180 into your calculator and go math, enter, enter. But 5 goes into 180 36 times. 15, I want to say it's 5 over 12. Is that right? So x is equal to 5 pi over 12 rads. Now, I'll ask you a question here. Is it easier when we sketch this to think of 5 pi over 12 rads or 75 degrees? I think 75 degrees is the simpler thing to think about here, isn't it? So all we're going to do is draw, I didn't hand out the rulers, don't worry about it. Draw a terminal arm that we believe is at about 75 degrees. The general practice is you don't have to draw in the initial arm. But you do need to label this. And I'm going to write it as 5 pi over 12, but if you wanted to, you could put theta equals 75 degrees. Very nitpicky thing, but it's important for later. A rotation angle has a direction. So that arc I've drawn has an arrowhead on one end of it. And this is different than how we would draw reference angles. And we'll be reminded of that later. So make sure that you draw it exactly the way I have it. Negative 120 is, forget about the negative, is 120 degrees a multiple of a common angle that we're familiar with? Yes, it's a multiple of 60. And I'm going to, push you on this. You should know by now 60 degrees is pi over 3 rads. It's a third of 180. So this is negative 2 pi over 3. That's all we have to do is just think of it. If you wanted to, could you set up a ratio? Whoops. Could you say pi radians over 180 degrees is x radians over negative 120 degrees? Sure. When you cross multiply, you get negative 120 pi over 180. Negative 120 over 180 is negative 2 over 3. When I look at these two numbers, these two angles, you might be different, but I find it easier to think of negative 2 pi over 3. I start at 0 and I go negative 1 pi over 3, negative 2 pi over 3. That's the rotation angle. And again, if I want to, I could have written negative 120. That's not the point of the diagram. The point of the diagram is you know what to draw. Are we still okay here? Okay. Convert the following radian measures to degree measures. First of all, just look at A, B, and C. And you can see how A and B are different than C. A and B are rotation angles given as multiples of pi. Don't waste your time with a ratio here. Pi is 180 degrees. 3 pi over 4 is 3 times 180 degrees over 4. Pi is 180 degrees. We've done the conversion. Now all we have to do is calculate what that number is. Well, 180 over 4 is 45 times 3 is 135, yes? I think, again, it is easier, if you look up here, to locate 3 pi over 4 than 135. To locate did we say 135? I should write that down. To locate 135, I'm not saying it's an impossible task, but you have to start going, okay, how many degrees away from 180 is that? You've got to start doing some subtraction or something. When I say 3 pi over 4, I just do this. 1, 2, 3 pi over 4. I'm going to put 135 degrees here. I put radians in the first example because we converted to radians. In this one, we're converting to degrees, so I'll put degrees. And that's theta. Similarly, negative 11 pi over 6. Well, I'm just going to ask the question here. How many of you know, just with very little thought, that negative 11 pi over 6 lands here? If you look at my arm, negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 30 degrees shy of being negative 360. And when we label this, we can do that. And again, how many of you see, based on the diagram, that this is negative 330? Okay, you didn't have to do that. You could have said, well, you could have done that, right? You could have said, well, it's negative 11 times pi over 6, and I know that pi over 6 is 30 degrees. There's lots of ways you can arrive at the destination here that we call the answer. It's negative 330 degrees. Any questions with B? Now, what happens if you have this? And, I meant to change it. I just didn't get time to make these changes last night. I could have really messed with you and said, I'll use D. This. Is that 30 degrees? No, that's radians, right? Because there's no degree symbol. So we want an exact value here. We have to use a ratio. I'm going to choose to flip my ratio upside down, Because I think when you set up a ratio, it's easier for students, for everybody, to have the thing you want to find on the top. At this level, it shouldn't matter, but this way we're going to have x over 6.5. So I cross multiply, I get x equals 6.5 times 180. There are degrees on this 180, by the way, over pi. Is it 1170 on the top? It is. So you get 1170 over pi. This is degrees. And so this example brings up an important point, and I don't want to dwell on it, but it's just something for you to think of. Normally, when you see an angle and there's reference to pi, it's radians. But this is an angle in degrees that does make reference to pi. You're going to get used to these intricacies as we move on. How am I going to draw this? Well, I could say to myself that I know, if you look at my arm, this is about 1 rad. But I think this is, and then start counting off 6.5 of them. I think this is a case where you actually want to figure out approximately how much that is. By approximately, I mean we can go to lots of decimals, but it will always be approximate because it will be irrational. So now take your calculator and take that and put it in your calculator. Let's get a decimal approximation of this thing. Just don't know where my calculator is. Oh, it's hiding. There it is. So when you go 1170 over pi, do you get approximately 372 degrees? Okay. So that tells us it's about 12 degrees past 360. You certainly don't need to do this with your finger, but it is that, right? What is important here is when you draw the rotation angle, you show that it's a full revolution plus that little bit. And this is, it was positive, wasn't it? Yep. This is theta equals 1170 over pi degrees. Is that okay? All right. So I don't know, does anybody from My Math 20 maybe remember me talking about coterminal angles? Look at the word, coterminal. The terminal arm is the same for coterminal angles. And we need to start making a real distinction here between the terminal arm, which is the destination, and a rotation angle, which is how we get there. This is saying you can have different rotation angles that have the same destination. And the example I give you is 50 degrees and 410. Because if I were to rotate to 50 degrees and then rotate a full revolution past that 50, which is 360, I get 410. I hope it's not lost on you that 50 plus 360 gives you 410. Right? They're 360 degrees apart. So sketch a rotation angle of 60 degrees. Well, that's child's play. Anybody can do that. I think I've probably drawn something that's more than 60. A little note here for you that on exams you were allowed a protractor. So if you're ever asked to sketch something on a written response, I think it's worth the time to sketch it properly. We don't need to worry about that here. What are 2 examples of angles that are coterminal with 60? Well, I don't know. 420. Think about what I'm about to write here, or enter. This, by definition, has to be coterminal. Whatever this number is I'm going to get, I'm saying go to 60 degrees and look at that location, that terminal arm. but now add to that rotation of 60 degrees 11 full revolutions. And I'm going to be back in the same place. This is coterminal. This is coterminal. But if you add or subtract multiples of a full revolution, multiples means a whole number multiple, right? You're going to get coterminal angles. So feel free to write down whichever numbers you want, 420, 4020, 31, negative 3180, but make sure you understand how to get those numbers. Any questions with that? Okay, so this gets a little bit more tricky. Well, negative 275. This one's still pretty easy. Negative 275, let's see, that's negative 360. Oh, negative 270 takes us to here, right? Do that again. Negative 270, negative 275. I didn't do the coterminal part like this with the first example, but we could have done this. Negative 275 plus 360. That's a coterminal angle. Plus 360. That's a coterminal angle. Negative 275 minus 360. Minus 360. These are all coterminal angles with negative 275. And again, you can feel free to write down any of them. The important thing is you understand how we're getting coterminal angles. There's not one answer. There's an infinite number. Now, when we take a look at something which is radians, it's more complicated because we have to work as exact value in our answers in anything in this course. So we need to take, well, let's do 5 pi over 6. I'm really hopeful here that everybody knows 5 pi over 6 is there. If you look at my arm, 1, 2, 3, 4, 5 pi over 6. So that's theta. Coterminal angles, well, a coterminal angle would be 5 pi over 6 plus a full revolution. But now we're thinking in terms of 2 pi. Well, we want to simplify that. And if this were not trigonometrically related, I would have said, well, you need to find a common denominator and work with fractions. And that's what we're going to do, but we're going to do it differently. If we want to add to 5 pi over 6 a full revolution, we need to add 12 pi over 6. Because a full revolution is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You know, I suppose you could think just purely in terms of fractions and say I need a common denominator, so I have to multiply everything by 6. But 5 pi over 6 plus 12 pi over 6, or (5 pi over 6 plus 12 pi over 6 plus 12 pi over 6, or 5 pi over 6 minus 12 pi over 6, or 5 pi over 6 plus or minus any multiple of 12 pi over 6 is going to give you coterminal. So if I add 12 to 5, I get 17 pi over 6. If I take 12 away from 5, I get negative 7 pi over 6. My brain just locked up there for a second. If I take away from 5, 12, I get negative 7. If I take another 12 away, I get negative 19. Are you with me here? Okay, pretty easy stuff. Well, negative 3 pi over 4. Again, I keep throwing these diagrams at you because I'm hopeful that the more you see, the easier they become. That doesn't quite look like 45. I have this part of my brain that cannot draw 45-degree angles. I always draw it, and then I go, no, it's got to move it this way, and then I got to move it back. I don't know. So 3 pi over 4 is 3 pi over 4s, and this is in a negative direction. This is negative 1, negative 2, negative 3 pi over 4 theta. Coterminal angles are going to be found by adding or taking away full revolutions from that initial angle that we're given. And a full revolution is 8 pi over 4. Okay, so I just have to ask something. I really shaved the unit down and I took out some stuff that I felt we could get rid of. But at the same time, am I moving too fast? Okay. Because we're going to be done here in 5 or 6 minutes, okay, which is okay. So that would be 5 pi over 4 would be coterminal. If I add another 8 pi over 4, it's 13 pi over 4. If I go back to the negative 3 and take away 8, I get negative 11 pi over 4. And it's interesting because I was just saying to myself, I wrote negative 5 pi over 4, and I thought, well, that's not going to be in the same place. So let's just check it out. Negative 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, negative 11. So let's put this together now. There is something called the general form for a description of coterminal angles. So it's an expression that describes all of the angles that are coterminal with a specific rotation angle. So if I said to you, answer this question, what are all of the angles that are coterminal with 130, including 130? How would you do that? Well, you would say that all of these rotation angles, these are all coterminal, are equal to 130 degrees. And there's two ways we can write this. I would prefer to do this. I would prefer to say 130 degrees plus 360 degrees times n, where n is an integer. And I want to talk about the number system here because I think it's important. Your integers, I'll just write at the bottom of the screen, your integers are the positive and negative whole numbers, and they include 0. So I need to use the word integer here because I have to include 0 because the question says I need to include 130. And if I put 0 in for n, I'm adding nothing to 130, that's 130. And then I have plus, 1 360, 2 360, or negative 1 360, negative 2 360, so I get them all covered. It's not wrong to say instead that you can put the plus or minus as part of your description, and then you have to say n is a whole number. If you do this, that would be wrong, because a natural number is a number like 1, 2, 3, etc. It doesn't include 0. And in this question, we're asked to include 0. So I have one more thing to talk about here. Whole numbers are 0, 1, 2, 3, etc. If, and this is subtle, but I've seen it on diploma exams, and I think it's dirty, I think it's mean, that if I said express the angles coterminal with, well, I'll do this on a different screen. If I said instead express the angles that are coterminal with 130 degrees in general form, this is really dirty. 130 degrees is not coterminal with 130 degrees. Because a coterminal angle is a different angle that has the same terminal arm. So if you were ever asked this, the coterminal angles, you pretty much have to write the following. You pretty much have to write that. Because this is saying we do not want to include 130. It's a rare event. It's like seeing a white elk out in the wild. You may live your whole life and never see it. But just in case. And I think it's a good exercise to understand the difference between natural and whole numbers and what's going on here. It's such a subtle thing that, and I'm not giving you any questions from your textbook because we're not using it this semester, but in your textbook, the author, not that they make a mistake, it's a subtlety they don't consider sometimes. They use natural when they should be using whole, or whole when they should be using natural. Anyway, this is the correct answer. What about this? This is so simple. Your coterminal angles will be equal to 7 pi over 3 plus 2 pi n, where n is an integer. You're adding or subtracting full revolutions, multiples of a full revolution. So n has to be an integer. Because I'm saying integer, I'm including the plus or minus in here. Integers include 0, so I'm going to get 7 pi over 3, and the question says we need to include 7 pi over 3. You don't need to simplify this, we're done. If you wanted to, you could put plus or minus and then say n is a whole number. That's it. So it went okay? There's a lot to take in, a lot of little details, but they're the building blocks of what we're going to be working on in the coming weeks. So on pages 4 to 5, I renumbered it. Is it still 4 and 5? Yep. On page 4 to 5 of your handout, there are problems dealing with coterminal angles, rotation angles, converting between radians and degrees.